All right, let's talk about how we can actually represent where charge is located on an object. So if you have an object and you want to know where is the charge located and how much charge is located in different areas, the representation we're going to use is called a charge diagram. It's a representation depicting where charge is located and what type of charge is present throughout an object. And the best way to explain what a charge diagram is by using an example. So let's say that I have a uniformly charged wire with one end at x equals 0 and the other end at x equals L. And I want to sketch a charge diagram of the wire. So I've drawn my wire here. I've got one side at x equals L 0, the other side at x equals L, where L is the total length of my wire here. And it's uniformly charged. So what that means is I should have charge located uniformly throughout the wire. Let's say it's positive. So I'm going to start by drawing a plus sign over here, and I'm going to try to draw them equivalently spaced, which might be a little difficult, but I'm going to do my best. So pretend these are all uniformly spaced. Let's go to the end here. That's probably fine. So there's my uniformly charged wire. And now another question that I might be able to ask is, what's the charge density? So find the charge density if the total charge is Q naught. So say the whole wire has a charge Q naught on it. Well, I know that because it's uniformly charged, I can take the total charge and divide it by the total length to get my linear charge density. So in this case, this one's nice and simple. My lambda is Q naught divided by L, where Q naught's the total charge, L is the total length. Okay, great. But you might ask, like, what if the charge density isn't uniform? That's all well and good, but sometimes your charge density might not be uniform. So what I'm going to do here is I'm going to erase some of these plus signs, and I'm going to change what the distribution of this charge actually looks like. So maybe I actually put more plus signs in here, and then maybe it starts to be more evenly, sparsely in the middle. Maybe there's nothing here for a little bit, and maybe there's some negative charges that start to pop up. And then maybe they get denser, too far, as we get to the end. Let's put another one here. All right, so now you have a non-uniform distribution of charge on this wire, right? You've got a lot of positive charges over here, not so many charges in the middle, and more negative charges on the right-hand side here. Well, if you want to calculate lambda of x, you have to calculate it locally. What this means is I now need to use this form of this equation, lambda of x is equal to dq over dx. And the reason I'm doing this is because your linear charge density at any individual x location along this axis here might be different depending on where you are. So let's say I've got this little box. I'm going to draw this little box. I chopped this wire up into this little piece, and it has this amount of charge on it, dq, an infinitesimal amount of charge. And that little chopped piece also has a width dx. Well, then I can take that dq, divide it by that length to get my local lambda of x. And now what we can start to think about is, what if I were to instead chop it here, let's move it over here, and now that dq will be negative, and my linear charge density is going to be a different value at this new location. So this is how you might start to tackle calculating your linear charge density using a charge diagram to help you understand where the charge is located and what charge is located where.